Hello everyone, welcome to the Structural Geek. We are discussing retaining walls today. So retaining walls are the structure or the walls which are provided when there is earth on one side of and there is no uh, earth or soil onto the other side on the same level. So let's take an example of this particular wall over here, which is shown in black. And on one side we can see that the soil is there, and the other side, which is let's say inside of a building or maybe like a boundary wall where we don't have any earth. So, in other words, we can say retaining walls are provided to retain earth from one side to the other. So, we don't want the soil or the earth to go in that portion of the area. So, that's why we need a structure which can retain this particular soil onto that side and bear the pressure that is coming from this. That is the basic function of a retaining wall. Namely, there are few types of retaining wall that are used based upon the way it functions, based upon the way the structure of the retaining wall behaves. Here are few type of that retaining wall structure, which is a cantilever structure, cantilever retaining wall. Here you can say that retaining wall is independent, it's not connected to any other structure per se, and it's behaving purely cantilever, having a fixed connection at the base. We have a soil on one side and this we don't have anything on the other side. This is the most commonly used retaining wall that you will find. Similarly, there is another type of retaining wall that you can have, that is propped cantilever retaining wall. If we take few example of cantilever retaining walls, I think boundary walls are essentially a very best example of cantilever retaining wall, which is the most commonly used, and the way they behave is purely cantilever. Similarly, let's take another example or another type of wall that we have, that is called propped cantilever retaining wall, which is a retaining wall which is connected at the top with a slab that is coming on a certain level, and you have a connection at the base which is also fixed. So it's like a propped cantilever. We have a soil on the other side and we don't have soil on the inside, and this is how it mostly behaves. The way it functions, that these type of structures that you can find is mostly in a basement or single basement or multi basement area, where you have slab being provided on one side. Structure in itself is not purely cantilever, it is having a connection at the top level as well, and a fixity at the base. So this is a one type of structure that is provided in retaining walls. Then you have another third type of retaining wall, which are called counterfort retaining wall. These structure that you're able to see over here are actually called counterforts, or which are actually supporting the retaining wall. And this particular retaining wall, rather than acting as a single 2D frame, acts as a two-way action, which is the soil that exerts the pressure on these walls is basically being taken by these counterforts. We'll be taking these things in detail in the subsequent part of this particular video. This list of the retaining walls which we have just discussed in terms of types is not exhaustive. There could be multiple other types of retaining walls in terms of way of construction, way of material that is being used, way of technology that is being used. The idea of this particular video is to just summarize what different type of structural behavior retaining walls can have in terms of grounding the forces that is coming on to them. So let's move out to see what type of loads do the retaining wall gets, and then we'll be seeing that how each one of these retaining walls take those forces to the ground. So what sort of loads do we have on the retaining wall? Mostly it's dead load, live load, earth pressure, water pressure, and the live load surcharge. These are the commonly found loads on the retaining walls. Dead load is the most common, that it usually gets from the dead load or the self weight of the structure itself. So let's say if the retaining wall is of concrete, the dead load that it exerts, that will be one part of it. The soil load that it also gets as a vertical load is also taken as a dead load. The self weight of soil will be termed as dead load. Live load is usually very seldom found in cantilever retaining walls. In cantilever retaining wall, there would not be any chance of getting live load per se. If there is, let's say, a localized portion where some columns are being supported on the live load, then you can get any live load on the cantilever retaining wall. Otherwise, live loads are not found. But you can get live loads for a prop on a prop cantilever retaining wall from a basement level. That's the typical location where the prop cantilever retaining walls are used. Then you have earth pressure. Earth pressure is the most common and most critical thing that the earth retaining wall are used to sustain. That's the most critical. And also, if the water level of the retaining wall is actually above the level of the foundation of the retaining wall, then you need to consider the water pressure as well. And also, let's say if this side of the retaining wall is having the soil and there is a possibility of movement that can occur in this side, let's say some vehicular movement or even any occupancy movement that can occur in this place where we have the soil, so that retaining wall needs to be checked for that additional live load surcharge as well. The earth pressure, now we can take each of these forces and see how each of these things actually affect the retaining wall, and then we will be seeing for each of the type of retaining wall how do they sustain that load and get stabilized during that particular thing. So dead load is actually favorable in when it comes to the retaining wall, because it is actually stabilizing the structure. Dead load is usually comes from the retaining wall stem. This part of the retaining wall is called stem, and also it comes from the base slab. So it is the vertical dead load that is coming. Live load is very seldom found. Earth pressure is again depends on the what natural ground level is and how much of the earth pressure it needs to sustain. So it varies as a linear fashion from as with respect to height, and it exerts the earth pressure on it. The actual quantitative values of the earth pressure we are not including in this particular video. Similarly for water pressure is also applied as per the height. Let's say whatever the water level of the is coming, if the let's say water level is coming up till this side, then beneath this we will have to consider the water pressure being exerted, assuming this as the zero level of the water. Then also the live load surcharge, whatever load that we are getting uh, in at this location as a live load, the horizontal component of that particular live load needs to be applied onto the retaining wall. So basically whatever horizontal loads, these three loads that we are having are actually horizontal load, and these are actually destabilizing the retaining wall and taking these are taking the retaining wall away from its position and trying to move it away, whereas the vertical load that we have, which is dead load, are actually helping to stabilize the structure. So overall stability of the retaining wall works like that. Now we'll be taking each example of cantilever retaining wall, prop cantilever retaining wall, and also the counterfort retaining wall, and see how do they stabilize these forces that are actually coming onto them. The very first type of retaining wall that we are taking is cantilever retaining wall. Here you can see in the image that onto the left side of the wall is the soil that we are having, and it is basically exerting a horizontal load as terms of an earth pressure onto this particular retaining wall. And this we have on inside where there is no earth. So if we try to make a 2D frame model of it, or like analytical model for this particular for so if we try to take this as an bar representation and make a 2D frame for this, so it will be something like this, where it's fixed at the base and it is getting a horizontal load. So what loads does it generally have? It is basically having an earth pressure, and which will generate a horizontal force at this location, a horizontal reaction it will generate. It will also generate a moment that it need to take at this particular location. So that will be the reactions from the ground, right? There will be few vertical reactions as well, but that will be mostly from the dead load that we have. This is essentially a bar representation, but if we come on to the actual 3D retaining wall, it will be looking something like this. So what all do we need to check in terms of the stability for this particular retaining wall? The first thing is that the horizontal force, which is basically coming from this, the retaining wall needs to take that. So whatever horizontal force that we are getting, that will be coming from the all the horizontal forces that we are getting, which is the earth pressure, the water pressure, and if there is any live load surcharge as well that we are having. So all the live load that it is getting, it needs to take that. So let's say that force comes out to be a certain value of the horizontal force at this location, and then the surface resistance or the resistance from the ground needs to be at least that. And in fact, as per the codal provision, we need to have a certain factor of safety based on that this force of sliding needs to be, the resistance of sliding should be more than of a certain factor with the actual force that we are getting. Similarly, if we get to the overturning, there will be an overturning for this particular moment that it will generate, that we will have the overturning of this particular force that is coming, the overturning moment needs to be sustained by the dead load of the structure itself, which is the stem, the base slab, and also the soil weight itself if it is helping. At times the soil load can soil weight can be destabilizing as well, and overall these two things are will be termed as a resisting moment. So for sliding check, what you need to ensure that resistance from the ground that you are getting should be at least more than, with a certain factor of safety, from the horizontal force that we are getting from the this cumulative F that we have got out of these three forces. Similarly, we for overturning we need to check if we need to check that the overturning moment that is being generated is less by the bursting moment that we are getting from the dead load of soil, dead load of concrete walls, and dead load of concrete slab that we are having at the base. Further, the sliding at times might not be able to be done with the help of friction itself. So at times those shear keys are also provided at the base to increase the resistance of the soil against the ground. So this is the way of actually increasing the sliding capacity. Further, if we look closely for the base pressure check, how does it happen? Then when the horizontal load starts to put at this particular place, at this particular location, let's say let's take this particular wall over here. So for this particular horizontal load, we will have a base pressure being generated in this fashion. Whether for we have a vertical load, we'll be having a base pressure which is uniform for that particular case, and also we'll be having a base pressure because of this horizontal load, which is basically uh, this part of the structure or the base will start to lift up, and here we'll be having a more compression that will come something like this. So overall we need to check whether or not the base pressure is okay, or is it generating the any loss of contact for us. So overall base pressure will be basically part of two components, which is P by A, which is actually the because of the vertical load, and the plus minus M by Z. M over here will be the overturning moment that we have got, and Z will be the section modulus of base. So let's say for this negative moment, we will be getting a lesser value, which is P by A minus M by Z. That P by A minus M by Z, if it is turning out to be overall negative, there will be a loss of contact, and we need to ensure that whether for that loss of contact that we are having, whether or not the the base is okay with the reduced width that we'll be getting on the base. Similarly, for the P by A plus M by Z thing will be more compression that we need to ensure if the base pressure is less than the bearing capacity of the soil or not. So which is basically for cantilever retaining wall, the stability checks becomes more and more critical, and sliding and overturning are one of them, and also we need to ensure the base pressures are okay. Now we'll be taking the next type of retaining wall, which is the prop cantilever retaining wall. Prop cantilever retaining walls are more or less similar to a cantilever retaining wall, but this particular support that we get at the top of a retaining wall is actually helps and makes this type of retaining wall bit simpler and easy to design when it comes to stability checks. Here you can see an example where we are having soil on one side, and there is a at the top we can see that there is a slab coming from this side, and also at the base we are having a fixity. The bar diagram, if we try to have this particular this or a 2D frame diagram, it will look something like this, whereas fixity at the base and we are having a horizontal support which is basically being taken by this particular this. Here it is actually critical to know that this can mostly take compression. Much tension forces are not being taken in this particular support per se. If we try to look at the how what the type of bending moment diagram will come out to be for horizontal forces. So let's say if the earth pressure and the water pressure that we are getting, and also the libra surcharge will come out to be something like this, the moment diagram for this particular case will look something like this. So which is basically the fixity at the base is actually is there, but since because of the fixity, we are having a fixed moment at the base, and at the top we are having an horizontal moment. The thing why it becomes less critical when it comes to the stability checks for prop cantilever retaining walls, because not all of the forces are being pushed into this through this connection. So we are having a few of the forces which are being pushed through the top support as well, or the top diaphragm. Since that top diaphragm is taking few forces, not check for the full force whether the sliding will occur or not. We can check for the reduced force which is being taken by this particular case. Further, there is a redundancy in the system that the above diaphragm can take more loads and push it into the adjacent wall that we are having in the same direction. Similarly, the overturning becomes less of an issue because the entire wall is connected at the top. That's something like it. Further, these type of retaining walls are also most common, or will be more found when you will having a multiple basement level. So let's say if you are having three basement, the frame system will look something like this, which is fixed at the base, and then at multiple levels it looks something like this, and at the top also there is another basement level, so it looks something like this. Yeah, and the moment diagrams for this will be something like this, which is like a fixity at this, and then you'll, since it's a continuity, you will be having fixity at this location as well, fixity at this location as well, and essentially a zero moment at the top. So it's like a multi-span continuous beam having a fixity at the base or one end. Basically, that's how it usually works in most of the cases. Although we need not ensure the sliding and overturning in this case, but the base pressure are still essential. The overall base pressure needs to be checked, and if ensured that whether it's okay for the given loads that we are having. So whatsoever base pressure profile that we are getting, we need to ensure that if the base pressure are still okay, or are we getting any loss of contact. And here in this particular case, for both cantilever and prop cantilever, I am not discussing the design part of it. We are only discussing up until now how the forces are being analyzed and how the stability concerns in terms of the wall are being taken, what type of load transfer mechanism is there. Now we'll be taking the third type of the retaining wall, which is counterfort retaining wall. The third type of retaining wall that we are having is counterfort retaining wall. Counterfort retaining wall could be basically an extension of a cantilever retaining wall at times as well. When for a long length retaining wall, if we are having very high deflections and we need to control them, counterfort retaining walls are also used. But let's first understand how does it function. So which is basically, in this particular case, if let's say this is a counterfort retaining wall and having a soil on this side, either the counterfort can be on inside as well, but it usually doesn't function properly and is not good as well in terms of functioning perspective. So it's always good to have counterfort onto this side, on the soil side itself. And when whatever forces that are being pushed from the soil side over here, earth pressure, live load surcharge, how it happens, let's say if we are having a very long retaining wall, and let's say if this particular, in this particular case, if these particular retaining wall starts to deform in this particular direction as well, because as of now, when we are when we are looking at the retaining wall, we are mostly working in a 2D fashion. We are only looking how it is actually behaving in in this direction, which is basically along the height. What about in the length? So in the length of the retaining wall, it can also bend when it is being pushed for that longer span, so that could create a problem. So the the way to treat it is that you basically provide counterforts. In this case, how essentially is happening, that the earth pressure is being pushed on this particular wall panels which are over here, and those wall panels are transferring the forces through reinforcement or any other mechanism or whatsoever the type is, through these counterfort, and then counterforts are taking this as an in plane load being pushed onto them as a push pull action. So let's say if you're pushing this counterfort in this particular direction, so if you try to push it, there'll be a pull in this particular case and there'll be a push in this particular case. So the idea that you need to understand in this particular location, that the entire horizontal the entire wall that we are having over here is getting an earth pressure, water pressure, and all the horizontal load, and that horizontal load are basically being taken by the counterfort as a push pull action and getting an in-plane load that we are getting onto them. That's the fundamental difference. In this particular case, the retaining wall at the base need not be fixed as well, this part of retaining wall, because even having a pinned connection over here can help, because this pinned connection that we are having will give you a push-pull effect and you will be able to stabilize the forces that we are getting, right? This is essentially the type is. If we try to understand through this particular diagram, let's say I've made, so this here a 2D frame diagram won't be used, we'll be having a 3D sort of a diagram. So the load transfer is such, which is basically we are getting a horizontal force on this surface. That horizontal force is being applied as a one-way action. Let's assume there is no load that is being taken by the bottom, because we are saying that there is no fixity at this place. So from the wall itself, so which is basically these are horizontal panels transferring the loads to the counterforts, and the counterforts are further transferring those loads as a push-pull action, pull at this particular on this side and push in this particular side, and transferring the loads to the bottom. So this is how the load transfer for a counterfort retaining wall occurs. This can also be needed with a fixed connection as well. Well, basically, let's assume that you have a very long retaining wall that is cantilever. You have designed it as a boundary wall, which is cantilever that you have designed it. And since it's of that large span, although you have designed the section as along the height, it could happen that because of that long span, it could start to deflect in the horizontal direction, and it starts to give a two-way action as well. So that for that to control, you need to give counterforce as well at times. So this was a small part that I wanted to bring forth on counterfort retaining wall. These are also very important and at times used to control the deflection in cantilever retaining wall. And in general, counterfort retaining walls are also a good way to retain earth, since it gives a lesser reinforcement in the connections and at the base as well, but it introduce few more structural members as counterforts as provided in this particular image, as you can see. So this was a small video on retaining walls where I covered few types of retaining walls and what loads do we have. If you like the video, please press the like button and subscribe if you want me to make more such videos.